Moving on to question 43. In the following sets of resonance forms, label the major and minor contributors and state which structures would be of equal energy. So in the case where there is equal energy, I just drew an equal sign in between the atoms. So in the following resonance forms, label the major and minor contributors. So I highlighted the major contributors. Why did I highlight nitrogen as a major contributor? Well, if we recall from the Pauling electronegativity scale, nitrogen has higher electronegativity, which means that it has an easier time carrying the extra electrons than carbon would, as shown here. And it's also shown here 2.5 for carbon versus nitrogen at 3.0. Moving on to B, we have an electron-rich oxygen, still electron-rich oxygen. There would be, this would not be equal, but I drew Y. We see an electron-rich double bond, we see an electron-rich carbon here, but between these two structures there's actually a third structure, which I have here on the right. It's this compound here, which has no charges on any atoms, which would therefore be the most stable. It would be the major contributor. And then to C, I have an electron-rich oxygen here. I see an electron-rich carbon here between the two oxygens. So I would say that yes, this would be the most common structure, just because the oxygen also has a very high electronegativity from the Pauling electronegativity scale. There's also a case that either oxygen can hold the partial negative charge. It doesn't have to flow any one way, it can flow either way from this initial starting point. You're actually going to see this structure again later. Maybe not here, but later in the textbook. What do I see in this case? I see an electron-rich carbon here, and then I see an electron-rich double bond, electron-rich carbon. So what do we see? We see the electrons flow from this carbon to form this double bond, and flow from this double bond into this carbon. What else can I say? From here, actually, between the two structures, they would be equal, but there's also a third major contributor in the form of the nitrogen. The electrons could actually flow to form a double bond into the nitrogen, which allows the nitrogen instead to carry the partial positive charge, which is okay because it has two attached oxygens also donating it electrons. Moving on to D. Oh, that was D. Moving on to E. What do we see? We see a lone pair on nitrogen. We see an electron-rich double bond. We see a partial positive charge on this nitrogen. I would like to take in this double bond. That also implies that this electrons are free to move into this space, because these electrons are free to move in this space. And then we see a partial positive charge on this carbon here. I'd say that the nitrogen is definitely more likely to carry the positive charge. I retract my statement earlier, and I'd say that this is the most important resonance form. As far as knowing resonance forms off the top of your head, that's not nearly as important as recognizing how many nitrogens, let's say, how many electrons are available on nitrogen, how many electrons are available on oxygen to even form double bonds. You have to recognize that they are electron-rich species that can donate their electrons to form double bonds.